on Sunday about Majoranas, and I just want to say that there is absolutely no overlap between what I'm going to talk about today and what I talked about then. So if you haven't come, you didn't miss anything for that. So what I want to talk about today is, I call it spin superfluidity and graphene in a strong magnetic field. And this is basically, I'm talking about work that was done with So Takei, who's here, and Yaroslav Chakovniak, who of course is here as well, and Amir Yacobi, who's not here. This work was recently published in Phys Rev Letters this year, and there was also a part of what I'm talking about dates back to an earlier paper by the same group of people that was published in 2014. So there'll be basically three parts to my talk, first I'm going to tell you what we mean by superfluid spin transport, which is a phenomenon that can take place in an insulating antiferromagnet with U1 symmetry. Then I'm going to talk about, we're going to want to apply this to a kind of quantized Hall state in graphene, so I'll have to tell you about integer quantum Hall states and their realization of the so-called Canted Antiferromagnetic state in graphene, and then our proposal for trying to inject spins and detect the spin supercurrent in a graphene sheet. So, over here, sorry. Okay, so the systems I want to talk about are systems which have a rotational symmetry about one of the axes in spin space. We'll call it the z-axis, and it's often called a U1 symmetry. I want the Hamiltonian to have the symmetry, but I'm going to look at a state which spontaneously breaks that symmetry, and the simplest example would be an easy plane ferromagnet or an easy plane antiferromagnet, where the magnetization can point anywhere in the xy plane, and the energy is independent of the angle in the plane. And the characteristic of these models is that since the Hamiltonian has overall U1 symmetry, that means that the total spin in the z direction, as z is conserved, because that's the generator of the rotations, that's the generator of the symmetry. You can have things where spin is transferred from collective degrees of freedom to individual particle degrees of freedom, but the total spin is conserved. Now, the case I want to talk about is a little bit more complicated, but it's something that actually I think has been sort of referred to in some of the earlier talks. I wanted to think about a Heisenberg antiferromagnet with an external magnetic field in the z direction. So the Heisenberg antiferromagnet means we're talking about spins on a lattice which has two interpenetrating sublattices, such as, for example, a simple square lattice, where neighboring spins sit on opposite sublattices, and for simplicity, we can think about a situation where we have just nearest neighbor interactions, that is interaction between spins on opposite sublattices, which I might write as some a coupling constant J times the sum of all nearest neighbor pairs, Si dot Sj. That means that this is a dot product. That means it's invariant under rotations about any axis in spin space. So this has a full symmetry, which is actually SU2 symmetry. The ground state, at least classically, if J is positive, then the ground state will be spins pointing in one direction on sublattice A and the opposite direction in sublattice B. That maximizes the energy, minimizes the energy on every bond, and it doesn't make any difference which direction in space they point as long as they're opposite on the two sublattices. Now, what I'm going to be interested in is a situation where we add an external magnetic field, say in the z direction. That will, of course, break the SU2 symmetry. Overall, we have only a U1 symmetry left, the rotation about the z-axis. And what is easy to see, and I think is earlier mentioned indirectly in some of the other talks, is that what the ground state is going to want to do in this case, if the external magnetic field is not too strong, if it's very strong, then all the spins will just align with the magnetic field. But if the magnetic field is not too strong, then what it's want to do is form a canted antiferromagnet state where the spins will align in a particular direction. Basically, what will try to happen is that the nail vector, the difference between the staggered magnetic field, the staggered spins will want to rotate to a direction perpendicular to the applied magnetic field. And so you get, say, on sublattice A, we can have, say, spins pointing in this direction. Here's the z direction. In B, they're in this direction. So the net magnetization is the same on the two sublattices, and it points in this direction, but the difference magnetization is perpendicular to it. So the Nael vector, n, which is the difference between the spin A and spin B, is entirely in the plane, xy plane, and then there's an overall tilt. And this is advantageous because you can see that if I have a relatively weak magnetic field on, I gain an energy from the canting, which is linear in the magnetic field. The cost, and that means the angle that it will tilt will be linear in the magnetic field. I gain a linear energy. The cost in energy for this being deviating from being perfect opposite, the spins being opposite, is only quadratic. So it always pays to line up in this direction, whereas if the spins were lined up with, say, A in this direction and B in this direction, you wouldn't be able to take any advantage of the magnetic field. Okay, so when we want to describe this state, we can talk about an order parameter, which is a complex number, which is nx plus I ny, and we write this as n times e to the I phi. Phi is the phase in thermal equilibrium. Below the transition temperature, this n is non-zero. The phi can be anything. The energy is independent of phi. But if we want to minimize the energy, we do require that phi be independent of position. So all the spins are the sublattice on a sublattice are parallel to each other throughout the sample. If I introduce a gradient in phi, that costs an energy that's going to be proportional to the gradient in phi squared by symmetry, and the value of n. In general, will depend on both the temperature and the magnetic field, and will relax to some value given by the temperature and the magnetic field in general over some period of time, but the phase is indeterminate. Similarly, we can talk about the total magnetization in the z direction, m0, and this is conserved. So this is something which, if I'm in thermal equilibrium where I can exchange spins with the outside world, it will relax to some value, which will be determined by the temperature and the applied magnetic field. Obviously, there's no, it'll be determined by the temperature and the applied magnetic field. But of course, since it's conserved, if I am not disconnect from the outside world, I can produce a state where the spin is not in its equilibrium value, and it will stay there for a very long time. And more generally, we can look at systems where the magnetization maybe is not constant, but varies slowly in space from one point to another. And also, we can look at something where the phase phi is not exactly constant, but very slowly in space. And then we'll have some energy, which I can write, at least to a good approximation, as an integral over space over, first of all, we said there's going to be a term that's proportional to the gradient in phi squared. There'll be some coefficient rho s over 2. Rho s is a spin stiffness constant. It also is the same symbol that one would use for a superfluid density, and there's a very strong parallel between these, the superfluid and this U1 symmetric magnet. And then, of course, if I deviate from the equilibrium value, there's going to be an energy cost, epsilon of m, energy density as a function of m, where epsilon of m is some function which will, of course, have a minimum when m is equal to the equilibrium value m naught, and will depend quadratically on the deviation from this equilibrium. And now I can ask what about the equations of motion if I have if I set up something where m is maybe not uniform and phi is not uniform, and I claim that long wavelength fluctuations close to thermal equilibrium, I can really treat this free energy as a kind of Hamiltonian, and m and phi are canonically conjugate variables, because m is the generator that measures the SZ, which is the generator of rotations, and phi is the angle of rotation. And so you wind up with equations of motion in long distances, which are the mdt is the derivative energy with respect to phi, and d phi dt is minus dE dm. And if you use the form that we had written down before, you see that the mdt is equal to minus the divergence of a spin current, Js. Js is just rho s times gradient phi. And of course, this guarantees that if I integrate over all space, then the integral of the mdt is 0. That's conservation law that we want. And in addition, if we look at the phi dt, that's given by the derivative of epsilon with respect to m, and since epsilon is quadratic in m minus m naught, this becomes something. This will become linear, m minus m naught divided by some coefficient chi, which is the magnetic susceptibility, and we can call this deviation from m minus m naught over chi. We can call that it's basically a chemical potential for the spin. And this is analogous to the Josephson equation for a superconductor. And this mu s, it's basically the energy it takes to flip a spin. If it were a metal, then this with conserved spin, then this mu s is basically the difference in the voltage, the electrochemical potential for spin up minus spin down. So if I have a magnetic field on, well, without a magnetic field, even if I have a deviation in the chemical potential for spin up and spin down, so I may gain an energy from flipping from spin down to spin up, then this would give me a non-zero value of mu s. Okay, and I should say these equations hold at any temperature less than Tc, and they are exact in the long wavelength limit. Provided when we're talking about T different from 0, we must define our thermodynamic functions at constant entropy density rather than constant temperature. And this is something that dates back quite a while. I think deviation at finite temperatures was first something that I was involved in almost 40 years ago. And we were interested at that time in what happened near phase transition at high temperatures, and we were interested in, and the important conclusion is these equations say that even at relatively high temperatures, you get spin waves, which in an antiferromagnet, of course, have a linear dispersion, and that dispersion is just given by the square root of the spin stiffness divided by the susceptibility, even at high temperatures, and they're undamped at long wavelengths. And we were interested in spin waves at that time, but here I'm going to be interested in a steady state solution, an infinite solution. Sorry, in a basically a steady state solution, which is not oscillating in time, but where we can think about a situation, but still would be non-equilibrium, that can occur for example, I could have m could be a constant which is maybe not equal to m naught, but also the gradient of phi doesn't have to be 0, but let's think about an infinite system where the gradient of phi is some constant different from 0. So that means that Js is a constant, and dm dt is the divergence of Js, so that's 0. So the magnetization density, which is a constant in space, is also a constant in time. D phi dt is not a constant, is not 0, but but it's a constant because it's m minus m naught, and that doesn't change the function of time. So this phase will just precess at a constant rate, just like the phase of a superconductor in the presence of a chemical potential. If we have a finite, for an infinite sample, this would be a solution. For a finite sample, we could look for similar solutions in which Js and m will, of course, have to be determined by the boundary conditions. So we can imagine the following situation. So the pink area here is my Canted antiferromagnet state, for my insulator, and on the two sides I may have, say, conductors with a chemical potential difference between left and up and down. On the left, this spin chemical potential µL, on the left-hand side µr, which are different. And then what will happen is that in equilibrium, we'll get a steady state in which the µs should be a constant because there's a superfluid throughout this Canted antiferromagnet region, but there's going to be some spin transfer between this reservoir and this reservoir and this, and we have to we can assume that the rate of spins being transferred in the spin current across the surface will be proportional to the difference in the chemical potentials µL minus µs, with some constant that depends on this interface. We'll call that GL, it's a spin conductance. And similarly, there's one on the right, and we have to have conservation of total spin current. Total spin is conserved, so these have to be equal to each other. And then this looks just like an electrical circuit where there'll be a solution in which the total spin will be given by the difference between the left and the right with a coefficient GLR, which is basically the sum of the two resistances, or the GLR inverse is the sum of the two inverse conductances. And this µs will just adjust itself to get the right value. And this spin current will be independent of the length of this Canted antiferromagnetic region. That's the supercurrent aspect of it. Oops. What happens here? Okay, and just to compare it, if I was at a paramagnetic state above the transition temperature, then of course spin is still conserved, but I wouldn't have a supercurrent. So the rho s, rho spin stiffness is 0, but I would still get I would get a current, but that would be proportional to that's the usual kind of spin diffusion current, where you get a spin current that's proportional to the gradient of µs, and with some coefficient which would be conductivity, the spin conductivity. And of course that means that if I have a long system, eventually where the surface is negligible, then the conductance would fall off independent. It will fall off as 1 over L when the length of that region becomes large. Now, of course, there's some problems with this. First of all, of course, just like any supercurrent, it'll break down if the spin current becomes too large. Secondly, in practice, a U1 symmetry is never perfect, and in conventional antiferromagnets, you have problems because U1 symmetry is broken by spin-orbit coupling, which give anisotropy terms, might favor a discrete direction for n in the xy plane. That means that you would need to have a chemical potential difference larger than some threshold in order to get this super transport, and also the non-conservation means that the spin current will fall off if L becomes too large. But in a Canted antiferromagnetic state in graphene is something that's potentially an ideal candidate for this because graphene has very small spin-orbit coupling. It's all carbon, and also the anisotropy is very small because it's a hexagonal lattice, and that's also very good. Whoops. Good. So that's what caused us to look at graphene. How much time do I have left? No. Okay. Okay, so let me remind you about graphene. There's some comments about graphene already also. So graphene, as you know, the atoms form a honeycomb lattice. So there are 2 atoms per unit cell. They're 2 interpenetrating sublattices, just what we want. And if there's no magnetic field, then as you also know, the band structure is very peculiar. It has 2 Dirac points in the Brillouin zone, typically labeled K and K prime. Near each of these Dirac points, there's a linear spectrum, and a neutral graphene, if it's undoped, the Fermi level passes right through these points. And now, if we take neutral graphene, in fact, graphene in general, if we ignore electron-electron interactions, apply a magnetic field perpendicular, then of course you get Landau levels, but the Landau level, just as you do in, let's say, gallium arsenide, but the Landau levels have a different spectrum. You get levels, both positive and negative energies, and the formula is that goes as the square root of the magnetic field, and square root of n can be 0, plus or minus 1, plus or minus 2, plus or minus 3. Each orbital state is fourfold degenerate because in addition to the spin, plus or minus 1, there are the 2 valleys. And one introduces the valley index to tau to distinguish K and K prime. And if I consider the combination sigma and tau, there are 4 states, and we can call this a hyperspin. And the Hamiltonian is invariant under rotations if I ignore electrons within this hyperspin space. And so these are the Landau levels that we've just talked about, the 0 Landau level in the center, the plus or minus 1s. And in neutral graphene, by particle hole symmetry, basically the Fermi level sits right in the middle of this of the 0 Landau level, and the 0 Landau level is half full. There's equal numbers of electrons and holes, and that means that it's not a quantum Hall state. To get a quantum Hall state, which of the usual type, you'd have to have an electron. You want the Fermi level to fall in a gap, and that only happens if you have filling fractions of 2 electrons. So this is a net of 0 electrons per flux quantum. If I add 2 more electrons, then I can be in a gap. Or if I add 2 holes, I can be in a gap. Or 6 or 8, 6 or 10. So this is a peculiar. This would mean that you have only gaps at these peculiar filling fractions of minus 6, minus 2, 6. But in fact, that's not what happens. There are smaller gaps that do occur in all the integers, and those are due to the electron-electron interactions. Just as in gallium arsenide, it splits. The electron-electron interaction causes a breaking of the symmetry, and what would happen is that you get a Hartree-Fock type state in which if I have a 0, if I have two electrons per flux quantum in the lowest Landau level, that's what happens at nu equals 0, these electrons want to go into you pick out 2 out of the 4 SU4 states, and you occupy those states and leave the others empty, and that gains you a Hartree-Fock energy, and then there's an energy gap at Hartree-Fock to the next excited state. And that lowers the energy, so you do get an insulating type state with an energy gap at nu equals 0. But there are many possibilities for this state. You can pick the long-range part of the Coulomb interaction doesn't care which values you pick and which spin you pick. But there are short-range terms that do care. So, of course, the Zeeman energy will try to favor occupation of, say, spin up over spin down. There are also Valley anisotropy terms that come from when two electrons are in the same unit cell, they care about which valleys they're on. So those I'll call Valley anisotropy terms. And they also have come into play. And so what happens is that if I had no Valley anisotropy terms, then obviously I would just occupy the one spin state, and there'd be an energy gap, which would be the sum of the Zeeman energy, which is very small, plus the much larger exchange interaction energy. And you would expect this system to be naively, you would expect it to be an insulator, but there would be but in this kind of a system, what you would find is that there would be edge states that contribute to conductivity, and instead of being a good insulator, it would have a conductivity of order E squared over H, or conductance of order E squared over H. And in transport experiments say that that's not the case, and that in fact the ground state is not a spin-aligned ground state, but it's a Canted antiferromagnet, but it's a state which has some other structure in which the spins are not polarized, and analysis of the behavior of the electron conductance in large in magnetic fields, particularly when you tilt the magnetic field, suggests that the ground state is this Canted antiferromagnet state. This was proposed by Karakinov, and he's able to fit transport data. So that's what we're going to, there's not a direct proof that the ground state is this Canted antiferromagnet state, but there's indirect proof, and one of the aims of our experiment, the proposed experiment, is to try to show that the ground state is indeed this Canted antiferromagnet state. So what happens in the Canted antiferromagnet state is that there's an electron. There's this, the electrons in the lowest Landau level tend to accumulate in a way that on one of the sublattices the spin is pointing in say this direction on the A sublattice, and the B sublattice is pointing in the opposite direction. So the spin density is very small, the electron density is very small, but the net difference from zero is given by this symmetry. So I'm going to skip this. Well, let's see. How much time do I have left, actually? 5 minutes? 3 minutes, okay. So, okay, let me, that was a discussion of what the edge states look like. So what happens in the case of the Canted antiferromagnet state is that the edge states open up, because spin is not conserved. If spin were aligned, if spin were conserved, you'd have an edge state which would have a left-moving edge state with spin down, let's say, and a right-moving edge state with spin up, and you get conductivity. But in this Canted antiferromagnet state, because spin is not conserved at the edge, because it can be mixed, because the spins are not aligned with the z direction, you've broken the symmetry, you open a gap, and this should be an insulator. Okay, so now, how do we try to create, detect, and detect spin currents in Canted magnetic state? So what we propose to do is to construct a gated, to use gates to control the densities in different regions of the graphene, so that it looks something like this. We have, here's my region, which is my Canted antiferromagnetic state, which is a good insulator, and it has no edge states here. This is the vacuum out here. Then we have a gate that depletes the electrons here from the lowest Landau level, so we have a filling fraction -2. We've taken out 2 electrons, there's nothing left. And here we have nu equals 1, here's nu equals -2, nu equals -2, 1. Okay, and then we have contacts. Here's a contact here, a contact here, a contact here, and a contact here. And we're going to apply voltages between these two contacts and measure the voltages here. And now what's going to happen is that electrons that are injected here, this is a quantum Hall state with nu equals -2, so there'll be two edge states here, both moving in the same direction, one for spin up and one for spin down. Let's see, we can see this in the next one. So the boundary between the nu equals -2 and -1 has to have two propagating edge states. That's how I get a Hall conductance of 2. The boundary between nu equals 1 and the vacuum that has a Hall conductance of -1, it has to have just one edge state, and we'll have just one spin in it. One of the spins, because the nu equals -1 state will be spin polarized, and that might be, say, the red state here with spin up. It goes through here, but the boundary between the nu equals -2 and -1 also has just one edge state. That will be the blue one. So if I inject an electron here with spin up, it will go underneath this gate and continue across here. If I inject an electron with spin down, it can't go in here, so it'll be reflected and just go back into the contact. And then finally, we can look at what happens at the boundary between nu equals -2 and nu equals 0. So again, there would have to be two edge states going in the same direction. And if spin were conserved, and if this were well aligned, then these would have opposite spins. There'd be a blue one and a red one. But because the nu equals 0 state has tilted spins, it can mix these states, and they won't be exactly up and down, but they can get mixed together. And we can see that whoops here. So they're slightly tilted, and if you scatter from one to the other, you can transfer spin from one edge to another. So what we want to do here is, in the experiment, oops. Okay, so what I want to do is put a different voltage on this contact and a different voltage here. So that means that the electrons that are incident on my nu equals 0 state here, if they have spin up, they would have come from this contact, so they have a voltage V up. And in this one, they come from this voltage, so they have a different voltage V down. So now I have, these two states are not in equilibrium with each other. They have different spins. Their chemical potentials are different, so there's an excess, let's say, of spin up over spin down. And what will happen as you travel around here or at these corners, or some of this extra spin can get transferred into the nu equals 0 state. That produces my spin imbalance, and that will cause a supercurrent, spin supercurrent to flow across, and that can produce a spin imbalance here. Basically, I'm going to cause my spins in here to precess, and they will pump a difference the steady state will have a difference in the chemical potentials for spin up and spin down that's produced along this edge here. And now what happens here again is that the spin up electrons will go into this contact, spin down into this, so I would measure a difference in the voltage between this contact and this contact, even though this is an insulator. So the point is that the point is that if I put the same voltage on V up and V down, there'd be no current at all transferred across, and I wouldn't know anything about it. It's only the difference in the currents that matters, and the difference in the voltages here is the only thing that I can detect through this insulator into a difference in voltages here. So that's because it's transformed by the spin. And just again, a picture of what's going on. We have this spin imbalance on the left, and that is transferred here. So we have this. These are the Nail spins here. These are Nail vectors, and we're going to cause a global precession of these that will then this global percentage should give me a time-dependent angle here that will pump, spin up or spin down, and lead to the imbalance on this side. Okay, so just as a summary, the experiment measures voltages and currents, of course, doesn't measure spins directly, and as we said, you're only measuring the difference in the voltages on the two contacts. Open questions, what we don't know yet is what is the dominant mechanism for spin exchange between the Canted antiferromagnet and the edge states at the boundary to nu equals -2. So we don't yet know how efficient that process is, but we believe it will be pretty efficient. And the other question is, of course, we've ignored mechanisms that can relax the spins, we think that should be very good in pure graphene, but of course if you have bad impurities with spin-orbit coupling and so forth, that could hurt you. And we don't know yet how that's going to work out. In any case, Amir Jacobi is trying to build, it's obviously a difficult experiment because you have to have all these gates and tune them, but he's working on that in his group. Thank you very much.
Thank you. Questions?
Yes. I have a question, sorry. I missed which is the Carnot constant in your Josephson-like equation, which is the proportionality factor. The proportionality factor that coupled the derivative time of the phase with the difference of bias.
Rho S.
Rho S. So it's not universal, right?
That's right. That would depend on the, yes, Rho S would certainly depend on a particular system. In an ordinary antiferromagnet, it would be very close to the exchange constant divided by the lattice constant squared or something like that.
I see. And why don't you think to do the exactly what you do in Josephson junction, that you do the opposite, the Shapiro steps? So you do the opposite effect to AC,
yes.
Generate.
So we have no junction. You say you want to you want to put on an AC
right.
field, which would be a resonant. So of course, yeah. So you could do spin. You could pump such a system. I think the equivalent is to say, well, if I subject it to an AC field that does antiferromagnetic resonance, I could pump a spin imbalance that would lead to a supercurrent. So I think that would be an analogy. Not an exact analogy, but yeah.
I have a question about the hydrodynamics that you put down.
Yes.
The hydrodynamics is just that of easy plane ferromagnet, it seems, right?
Correct, yeah.
And the experiment that you proposed seemed to be just this separately conducted quantum Hall bilayer kind of experiment, right? So
yes.
Right, that's exactly what you're doing.
Yes.
But that kind of answers the first question of open questions. The mechanism of spin exchange is call it spin transfer torque in magnetic language, or Andreev scattering in superconducting language.
Yes. Well, I didn't mean that it was. I just meant it in a quantitative sense. So let me.
I think I also mean it in quantitative.
So we don't, because spin transfer torque, you usually put in some kind of a contact resistance, is a G up. I mean, those numbers are to calculate them microscopically is not necessarily so easy. You have to know what the interface is like. So just here, so there's first of all, there's going to be spin transfer at these corners and also along here. In order to transfer spin here, you have to break momentum. There are issues of momentum conservation, for example, that make it actually not so easy to transfer from one spin to another, because they're associated with different valleys, and you have to have either some kind of impurity to take up the momentum. But it's not clear exactly what will cause relaxation along the bulk. Now at these corners, we know that we have that momentum isn't conserved at the corners. we have, but is it adiabatic? It could be that that you have a lot of that dominant transfer was going to occur at these corners, and very little transfer will occur along the line, or it may be uniformly distributed. And that's the kind of question that I think is not, unless you see an easy way of understanding it.
So the way I'm trying to think about it is just, as I said, Andrea, you have electron impinging in something, hole reflecting, and electron like Cooper pair entering. That's what's happened here with the spin.
Yes, but quantitatively, let's say if I have a junction between a normal and a superconductor.
Probabilities may be hard to calculate.
Yeah, that was the question. So what's necessary if you have a barrier? If you had a superconductor and a normal metal, let's say, which had different Fermi levels, then whether you transfer efficiently or reflect, you may reflect 99% by ordinary reflection and 1% Andreev, or it could be the other way around. And that has to do with momentum conservation and details of the surface. That was the point I'm trying to make.
Okay. So, one more question before break.
I guess it's also a follow-up question to this. If you want to think about this state in terms of usual understanding of antiferromagnetic dynamics and not in terms of your equations, how would you describe it in terms of, I don't know,
Magnons.
Uniform rotation, or how many magnets, or how are they?
Well, I think maybe it's easy to think about it in this picture. Let me think about something where this was a lattice of some kind with so what would this would be the nail vectors in adjacent unit cells, and they're coupled together by exchange constants. So if I try to twist, if I were to take one end of it and start twisting it, it would pull the others along. And so by twisting at one end, it will try to make all the others twist at the same rate. Now, of course, if I have dissipation and vortices and stuff, then one end might twist and the other end wouldn't twist. So that would be happening. I'd say at high temperatures, in the normal state, you could think about it as having a lot of vortices in here. So I twisted one end, and the neighboring ones would twist, but eventually it wouldn't twist because vortices would move across. But in the nail state, below the transition temperature, they would all tend to twist. So if I twisted here, eventually it will cause things to twist here. If these are twisting, it can do dynamic pumping of the. It will cause, at the boundaries, it will pump spins from one side to the other.
So, can you say that in this case the angles between those arrows remain constant as they rotate?
That's the spin. Yes, the angle. That's right. So if this here it's complicated because it's a two-dimensional geometry. So when you minimize the energy, it's complicated. But if this were ideal, where it was a one-dimensional geometry, so that all of these spins were aligned in the same direction, and then these would be in a different direction, then there'd be a constant gradient. Then the steady state that I would get by twisting, and with this, say I had some kind of a drag on this end, and I'm twisting on this end, then the steady state would be a uniform gradient of the phase. The phase would change by a constant amount, and that would correspond to a constant spin current. The drag here would be produced by say, interaction with a normal metal, where spins would be flipping, and here again, by obviously if I'm applying a torque, that means I'm not conserving the spin because of the torque that I'm applying. So
So it's the very last query.
So like this picture looks semi-classical.
Yeah.
In the language of spintronics, I could say that this flip is causing the torque on the first guy, and then I will just solve like a bunch of analogy equations to see how this propagates
Absolutely.
from left to right.
Correct.
There is also a quantum language of this, which is electron hitting a magnum, and then I have to consider diagrams basically to see how the two quasi-particles interact. So like, is there anything beyond the first picture that I would capture if I formulate this in the grammatic language?
I think if I wanted to look at what happens at finite temperatures for a finite system, in addition to the supercurrent, you can have a normal current, which would be a normal current of magnons that you might want to describe this way. Typically, if you have a long system, the normal current is going to decay. These magnons will scatter and they won't be very efficient. So your supercurrent will dominate the spin transfer. And I think it's only if you want to go beyond that supercurrent that you really need to worry about diagrams and do something complicated.
Okay, let's thank our speaker again.